Welcome everybody to today's lecture, which will be on optical spectroscopy. My name is Lars Rippe, and I think most of you met me when we were presenting the projects, and I was presenting Project D, which is about mid-infrared spectroscopy to detect low levels of substances in the atmosphere. Okay, so let's get started. So here we have a schematic picture of an optical spectroscopy setup. So let's go through and quickly discuss the different parts, give some example of what kind of parts we can have, and then we will dive into each part in a little bit more detail. So the first thing we have is a light source. And this light source sends out, on the same time sends out light over the whole region we are interested in looking at. So it's a broadband light source, and this is relative. I mean, it can be broader or more narrow, but the thing is that it sends out light over the whole wavelength range we're interested in at once. After that, we have our sample, so that's our spectrally absorbing sample normally, which has a particular fingerprint, so some of the colors the light source sent out, they are absorbed or possibly emitted by this spectral sample. So if they are absorbed, they disappear from the light. So that means after we have passed the sample, we have less light. But by just looking at the light here, we cannot say anything about what particular frequencies or what particular wavelengths of the light went missing. If we want to do that, we need to in some way divide up so that we can see the different wavelengths individually. So that means we have to add a spectrally resolving instrument. So that's some sort of instrument which divides the different color of the light so it comes out in different positions or spatially comes out in different directions. And then finally we would like to detect all of these different positions at once, so we need some sort of detector who can detect the different positions the light come in simultaneously. Okay, so let's now back to the light source and give and then we have some optical components between the different parts of our setup, which is basically redirecting the light going through our setup. So let's go back and start talking a little bit about one possible example of a light source. So this here on the picture is a halogen bulb, and this is a blackbody radiator. So here we have the emission of blackbody radiators at different temperatures. As you probably know, the hotter something is, the more radiation it gives off. But the hotter it is, it also shifts the peak of where the radiation comes out. So if we have something which is cold, for example, here we have something at 79 Kelvin, that has the center bit somewhere between 10 and 100 micrometer. While if we move up here where we have a sun's temperature, which is 6000 Kelvin, it has its middle of its emission somewhere in the visible range. So, just sort of in the red range of the visible range. So the hotter it is, the more light it gives out and the more visible light it gives out. So we'll come back and talk a little bit more about halogen bulbs. But they have as you can see here, the halogen bulb is about 3000 Kelvin, and that has quite a large emission in the visible range and going into IR slightly over 1 micrometer. But it's a very broad, and as we shall see in the next slide, it's also a very even emitter, and I will talk more about that in the next slide. Okay, so let's continue and look at our spectrally absorbing sample. So that's this part over here. And in this case, as an example, I have a spectrum of liquid water. So at low wavelengths, below 200 nanometers, liquid water has very strong absorption. And then in the visible range, the absorption drops, and we can see here between we have the lowest absorption here for liquid water. at about 500 nanometers or so, and then the absorption goes up again. And here we can see that we have some spectral features which we might use. These spectral features here, for example, we could use to look at the fingerprint of this material. So if we see something with exactly this fingerprint, we know that we have liquid water. But as I said, after we have passed this sample, the only thing we can see if we look here with a detector is that light is missing, so there's less light. If we don't have a spectrally resolving instrument which can detect what colors disappeared, we can't really say so much about exactly what was in the sample. So now we want to divide the different colors of light so that we can detect them. And one way of doing that is by a prism. So here we have a prism which has different index of refraction, and we'll come back and talk more about index of refraction and why we have different index of refraction for different wavelengths. But since we have the index of diffraction means that the light will change angle as it goes through, and since we have different index of refraction for different wavelengths, that means that we will have different wavelength change we have a different angle change for the different wavelengths. So therefore, after we have gone through this example of a spectrally resolving instrument, we will come out so that different wavelengths are going in different directions. And you see here the blue and the purple ones are deflected more, and the red ones are deflected less. So now they are coming out in different directions, but now we would like to be able to detect how much light we have in these different components. Oh yeah, I have a picture of how we are dividing up the different colors here. So we see here we have all the light coming in, and then depending on what color the light has, it comes out in different directions. So then we go to the detector, and one of the most common detector around is a CCD or a CMOS chip like we have in our cameras, and this is of course a 2D detector. But in this case, like we set it up here, it would in principle be enough with a 1D detector. So if we put this detector over here, then for example the red light can hit the pixels in the top, and then as we go down the blue light can hit the pixels in the bottom. And this allows us to simultaneously measure how much red light we have, how much purple light we have, how much red, how much yellow, how much blue, and how much purple. And we can do this in many channels at the same times. And since 2D detectors are used for image acquisition, they are very common. But there are also 1D detectors. So that means here we have a row of detectors, and for some type of detectors which exist in a row like this have some properties which makes them good for spectroscopy, so they are also used. So let's start looking at some different light sources. But before we leave this page, let's just quickly look at the blackbody radiation and make the following observation. That if we want to do spectroscopy in the visible range, or here close to in the low IR range, which is where a lot of spectroscopy is done, you see that we need a fairly warm light source. So if we want to have an effective generation here, we would like to have 3,000 or 4,000 degrees. Here in the visible range, we would like to have 3,000 or 4,000 or even higher temperature. So let's just keep this in mind as we continue to look at different light sources. So the first light source we will discuss is a xenon arc lamp. So the xenon arc lamp, it works by passing the light in this is produced by two different mechanisms. So what happens here is that you have two electrodes, and in between these there's high pressure xenon gas, and you pass a strong current, you pass a high current through this xenon gas, and this creates a plasma. And this plasma emits light, preferably in the visible range, up to about 700 nanometers. And then this current, very strong current of electrons, it hits an electrode, and this electrode heats up, and above about 700 nanometers, this is the main contributor to the light emitted by this source. So the nice thing about this source is that if we see here, so this here is the xenon, this is the xenon light, which you see, which comes up here and has some features here, but it goes all the way down to low wavelengths. So it can be used all the way down to 180 nanometers. And then it's fairly smooth, so as you follow it up, it's a fairly smooth blackbody radiator with a very high temperature. So it's about 6,000 degrees warm, this plasma. So it's close to the temperature of a sun. And since it's so hot, that's why it's deliver light all the way down into the UV, all the way down to 180 nanometer. And then it's very smooth. And then when we come up to between 450 and 500 nanometers, then there's a little bit of spectral features. So these spectral features, they are emission lines from the xenon. And then above 500 and up to about 700, it's very smooth again. And then when we come up to above 750 or so, we get a lot of spectral features again from emission from the xenon inside the light. Another benefit from this kind of xenon light is that the light inside it comes from a very small spot close to one of the electrodes. So that's where you have this very hot plasma which emits the visible light. So, and that's good for some application, for example, like cinema applications. So these are often used in cinema, and another reason why they are used in cinema is because they can produce so much light. So they can be up to 15 kilowatts, for example, if you look in a IMAX cinema projector. So just to quickly recap, we have two different sources of emission. We have thermal emission from this very hot plasma, and the thermal emission from the hot electrode, which is at longer wavelengths. And then we have this emission from the xenon gas, emission lines from the xenon gas inside the light. And if you want to detect something where you have a strong emission pattern from the light source itself, that's of course much more difficult, because if you were to use the xenon light up in this region, that wouldn't be so easy because it has a very strong spectral feature itself, and then you have to be able to separate the spectral feature of your light from the spectral feature of a sample you would like to analyze. So for example, we also have a mercury lamp here, and you see the mercury lamp has a lot of emission lines from the mercury inside the mercury light. And that makes it for the regions where it has a lot of spectral features, one have to be fairly careful if one should use it for spectroscopy. So therefore, the different sources are predominantly used where we have a smooth spectrum. Our next light source is a halogen bulb. And just like the old type of bulbs you had at home, a halogen bulb works by passing a current through a filament wire. So that's a wire made out of some sort of conductor, a metal. And if you do this, if you pass current through the metal wire, it starts to heat up. And as it starts to heat up, it will start reacting more actively with oxygen in the atmosphere, which means that it will oxidize, turn into rust. And to stop it doing that, you put it inside a glass container where you can have an atmosphere which doesn't contain any oxygen. And then you can keep on heating up your wire to hotter and hotter temperatures, but you cannot make it. There's no material which can withstand as high temperature, or there's no material which can get to the temperature you had in a xenon light, which was in this plasma. The plasma was then 6,000 degrees warm, but there's no metal which can take that high temperature. So we first choose a metal which can withstand a very high temperature without melting, and that's normally tungsten or wolfram. And then we fill, in the case of a halogen bulb, we fill it with halogens. So halogens are element from group 17, so that's fluorine, chromine, bromine and iodine, and nowadays it's mainly hydrocarbon bromine compounds which we have inside these halogen bulbs. And to be able to explain why we have these halogen compounds inside the bulb, we first talk about what limits the temperature, because it's actually not melting. Because as you heat it up, your wire has small imperfections. So in some places it's slightly thinner than the other places. But you pass the same current through the whole of the wire. That means that in these places where it's thinner, it's actually going to get hotter because it's thinner there and you're passing the same current through it. And that means that there are more atoms which start evaporating away from that region. So that means that if you run a normal bulb too hot, it will soon become thinner and thinner at the thinnest portion of your wire, and it will break there. And that limits your temperature, how high you can have a temperature of your wire. But in a halogen bulb, you have gotten around this process in the following way. So in the first picture here to the left, the black atoms here, they are wolfram or tungsten molecules which evaporate from the wire. And when they come out, these atoms come out, they form complexes, that is molecules with the halogen compounds in the gas. So that's these molecules you see here. And these molecules, they are fairly stable. So that means that they don't break by themselves. And for the process which breaks them is that when they come in contact with the hot wire, they break, and then they deposit the wolfram or the tungsten back onto the wire again. And the likelihood of this process is proportional to how hot the wire is. So if the wire is thin and thereby hotter, it's more likely that it's going to deposit the atoms back, the wolfram atoms back. And that means that it has a self-healing process which smooths the wire out. So any hot spot is taken away. These halogen also stops the wolfram from hitting the glass. So that means you don't get a deposit of wolfram on the inside of the glass either. Okay, so next we're going to be discussing mode-locked lasers and supercontinuum sources. And here we're going to look at how, when you looked at lasers, you saw that they can be used as very spectroscopic, very precise spectroscopic tools, because you can make them very narrow band. And we will discuss this more in the next lesson. But now we will go the other way and show how we can make lasers really broadband, and by using nonlinear index of refraction. So that is an index of refraction which varies with the intensity. You can make them even broader, and this trick will actually be used twice, once for the lasers and then once to make them broader. But let's start off a little bit and looking at the imaginary laser cavity. So when you discussed lasers, you looked at if the lasers could possibly lace at many different modes, you could add components inside it to choose one mode. So you would add something which made sure the losses were really low for one particular mode. Now, you can also go the other way and not do that at all, rather try to get it to lace in many modes at the same time. So let us look a little bit what that could possibly look like. So here we have a cavity. So in principle we have a mirror here and we have a mirror here. And then we have different potential standing modes which could lace inside this cavity. So you see the lowest one here is this one here, which you see going up like this, down and then up again. And then you have the next standing mode, and so this is with half one, and then the red one, is the red one next? No, the green one is the next one with two nodes, so this one going up and now down here, and then the red one with three, and so on. So this is like a picture of a laser cavity lacing on several different modes at the same time. Okay, so this is where we look at all the different modes individually, but of course what you will actually see if you were to be able to look at this would be what is the sum of all these modes. And that would look something like this. So if we just sum all of these different modes up, which you see in the picture at the top, what you actually get, so you just sum at each point, and each time point you sum the E field. What you actually get is a short pulse like this. And as you see, this short pulse is then moving around inside the cavity. And let's now imagine that in one of these we have a mirror which is not 100% reflecting but has slightly lower reflectivity. What will then happen? Well, that means that every time this pulse hits this mirror, there will be a pulse emitted outside the cavity. So over here we have a picture. So again, we have drawn the different modes of a laser if they were to leak out one by one. And then at the bottom here, we draw what if we combine all these modes, what do we get? So we asked at every point here, we add all of these different up. So then you would see here that if you see this one is at its peak here, this one is at its peak here, this one is at its peak, and so on. So if we add all of this up, we get a very big electric field at this point. But then as we move out from this point, they have different frequencies or different wavelengths. So that means that they become out of phase. So if we look somewhere over here, this one is the top while this one is the bottom. So here they will cancel out and we will have no E field. Okay, so that means that we can have it lace on many different modes at the same time, and we can make very short pulses. Okay, so keep on going. Okay, so this requires a certain phase relationship between all of these different modes. In the picture down here, you see if you have a right phase relationship between all the different modes, you get these very short pulses. But if you have a random phase relationship between all these different modes, you get a variation in intensity, but it doesn't become short pulses with very high intensity. So we want to have some way of making it so that we can force it in to have this pattern with very short pulses. Because if we can get it to have these very short pulses, it will also be lacing on very many modes. If we have this thing here, it will actually most of the time just lace. It will lace on a number of modes, but it will generally lace on the modes which has the lowest losses. So we want to do a trick to get short pulses. And the trick we play here is the same trick as when you select a single mode. We want to make it so that when you have these short pulses, you have the lowest loss in your cavity. So the trick of getting lower losses when we have pulsed is noticing that we have higher intensity when it's in pulsed mode, because then all the intensity comes out at one time. And the duration of a pulse compared to the duration between the separation of a pulse in a real system can very well be a factor of 1 million. So that means that you have much higher intensity when it's in pulsed mode. So we want to create an intensity dependent losses. So let's look at how we do this. Okay, so first, if we have normal index of refraction, it's just a constant. But in some mediums, we have an intensity dependent index of refraction. So that means that we have a normal index of refraction plus some constant times the intensity. So the higher the intensity is, the higher the index of refraction. So let us now take a laser cavity. So inside the laser cavity we have our mode, and the mode here has higher intensity in the middle and lower intensity on the side. It's a Gaussian mode. And we send it through a crystal like this. Now what does this mean? Well, it means that in the middle where we have higher intensity, we will get higher index of refraction. On the sides, we will get lower index of refraction. And this looks just like a gradient index lens. So the higher the intensity is here in the middle, the bigger the difference is from the side, and the more we will focus the beam. And this leads to that if we have a pulsed laser with high intensity, this will be focused much more. And if we now introduce an aperture out here, cutting out the light from out here and only allowing the light which is focused slightly through, that means that we will have lower losses for when we have high intensities. So this is called a Kerr medium with intensity dependent index of refraction. And in many of the lasers used, actually it's the crystal where we get lasing also have a Kerr effect, so you can use the same crystal as your Kerr medium. And the only thing you have to do is set it up correctly and introduce an aperture. And then the noises in this, or sometimes you have to introduce a little bit of extra noise by knocking one of the mirrors slightly. But otherwise the noises that you actually have slightly higher intensity in some places will start making lower losses for the case where you have pulses, and then it will go towards having very short pulses. And these short pulses, the shorter the pulses are, the broader the spectrum you will have to create these short pulses, and the broader your laser is. Okay, so now you have created a laser which lasers over a very broad region, but you can actually broaden it even more. And then you will use this Kerr effect once more. So what we do now is we send it into a fiber, and inside this fiber, we have chosen a fiber which has high Kerr effect, so the same nonlinear index of refraction. And that means that now we look at the different index of refraction for different parts of the pulses. So here in the beginning of a pulse in time, we have slightly lower index of refraction, and then at the middle of a pulse we have slightly higher index of refraction, at the end of it we have slightly lower index of refraction. That means that this part which has higher index of refraction will be delayed more, and that will change the phase inside the pulse, and this is called self-phase modulation. So in self-phase modulation is when the different parts of a pulse experience different index of refraction, and this will also broaden the pulse spectrally. So here you can see that in the beginning this is a fiber. You see here it comes in a red laser, and as it goes through it gets whiter and whiter, and when it comes out here, I mean, it looks slightly bluish, but it actually contains all the different colors of light. And here we have an example. So this is a laser which runs at 1060 nanometer or 1064 nanometer, depending on what kind of laser it is, and it's a very narrow laser. So this is actually a mode locked laser, so it's not very narrow, but it's not so broad. You send it into one of these fibers and you get the following spectrum out. And here you can see you have light all the way from 600 nanometers all the way up to 1600 nanometers. So you have a very, very broad light source. So you might say, hang on, but you just said that it's many modes lasing inside this laser cavity, so that means that it's actually not continuous. And this is true. You actually have laser modes, and typically they're separated between 50 megahertz up to a gigahertz or so. But for many spectral applications, not all, but many optical spectroscopy setups, you don't consider these because they're so close together that you can just use it as if it was a continuous light source. And again, it's a continuous light source over a very broad region, and it, apart from this very fine structure, it can be fairly structureless. So it's a very suitable source for spectroscopy, and therefore it has lately become very popular. However, it's not a very cheap, if you compare to some of the light sources we looked on so far and some of the light sources we looked on later, it's not a very cheap light source. It's slightly expensive. So the next light source I'm going to talk about, it's synchrotron radiation. And as many of you are probably aware, on the recent year there has been a new big synchrotron facility constructed here in Lund, namely MAX 4. And the special thing about synchrotron is that they can have radiation with much higher energy than you get from the other sources we have talked about so far. So synchrotron can go all the way from visible, but there are many sources in visible, so the primary interest is that it can go all the way to X-ray energies. And the light in the synchrotrons are generated by accelerating electrons. So if you have an antenna inside your mobile phone, the way it emits electromagnetic radiation is that it accelerates electrons forward and back, up and down the antenna. So they are going up and down the antenna as they're being accelerated. They send out electromagnetic radiation in that way, generally in the microwave regime with a few gigahertz. Now in the case of in the case of synchrotrons, it used to be, you see, so here you have a round ring, and around this ring you have electron in bunches going around very, very close to the speed of light. So they are typically going with more than 99% of the speed of light, and even a few more nines after that. And that means that when they come to the corners, or rather this was how it used to be done, when you came to the corner, you change direction of an electron, you change the direction of a path of electron, and that means that you accelerated. So at the corners you would expect to get a donut emission. So here you have electron, it's being accelerated around the corner. You would expect to get a donut emission of electromagnetic radiation. This is what you would get out of an antenna. But since these electrons are moving so fast, they're very close to the speed of light, so then you get very, very strong relativistic effects. And what this relativistic effect is that they take this donut and they fold it together so that it looks like a beam coming out like this from where the electron is turned. And this beam is very, very broad in frequencies. And I say that this is how it used to be for the first synchrotron, this is how the radiation was generated. But nowadays it's actually the straight part of a synchrotron which is used to generate the light or the electromagnetic radiation. So what you have here is something called an undulator. And this is an undulator here. So what this is, the beam comes going through in between these two massive things here. And what is in these is magnets. So inside these is magnets which has either potential in this direction or the magnetic field in this direction, and then next set of magnet is in the next other direction, and so on. So every second pair of magnets are switched in direction. And when you send an electron beam through here, this magnetic field will change the track of the electrons. So as you go in between these, the electrons are accelerated first down and then up and then down and then up and then down and then up like this. And this is called an undulation. So you create radiation here, and then when you at a certain time distance you will be here and you create radiation, and then at a certain time distance you're here and you create radiation. And just like in the last picture, the direction of you're creating radiation when you at the turn here is straightforward like this. So you also generate radiation when you're turning when you have a maximum acceleration down here. So these are the points of maximum acceleration. So that means that there's a lock time and there's a lock distance between the different points where you create this radiation. So the radiation from these different points, they interfere. And that means that you get an interference where you can get much more narrow band radiations. You can get more radiation within the window you're interested in. And by changing the distance between these, you can change exactly where the radiation is generated. And you can also make different kinds of undulator which are made to generate this radiation in different regions. But sometimes you're actually interested in getting more broadband radiation. And what you can do then is you can increase the amplitude of these wiggles here. And then you get into something called a wiggler. So the difference between an undulator and a wiggler is that the amplitude is much larger. And as the amplitude gets much larger, it leads to a much broader spectrum.